Hey guys, how you doing? It's Jalaj over here again, back with another video from Be a Gem at GCSE Chem, and today we're going to be doing section C4.9, which is called Volumes of Gases. Now before I start, I want to say happy birthday to my teacher. It's Miss Khan. It's her, it's 25th of August. It's her birthday. She's a really good chemistry teacher, and she's teaching me A-level chemistry, and I want to just say happy birthday, and I hope you're having a great day. And that's all there is to say there. And and yesterday actually, after doing titration calculations C4.8, I gave you this question to do. There was the question was this. Sorry. The question was this one in the white box, because it's not a white box, but it's a white notepad, whatever. That was the question. Basically, you were asked to basically work out the concentration of sodium hydroxide, and because I went through two examples basically, and I wanted you to try out the third one yourself. I'm not really going to go through this in much detail, but basically in too much detail, because I've already gone through this section yesterday. But basically the answer I got was 0.80 moles per decimeters cubed for the concentration of sodium hydroxide. So make sure you got that. You wrote write the balance equation, write the information you're given for each compound. You might be given volumes, concentrations, then use number of moles equals concentration times volume to work out the number of moles of the sulfuric acid in this case, and then you compare the stoichiometric ratios, which was obviously 2 to 1. So if I got 0.01 moles for sulfuric acid, I then therefore doubled it to get the number of moles for sodium hydroxide. So I got 0.02 moles. I was already given the volume in the question, and I just used concentration equals moles over volume, number of moles over volume, to get the concentration of sodium hydroxide. So I'm not really going to go through this much, but there we go. I got 0.80 moles per decimeters cubed for the concentration of sodium hydroxide. And if you need to, if you don't really understand this much, it may have been because you wouldn't have maybe seen you probably didn't see my video that I made yesterday, which was on the titration calculations C4.8. So titration calculations C4.8. There we go, section C4.8. And in C4.9 today we're doing volumes of gases, and this is only for triple science students only, basically, and specifically for triple science higher students, not for triple science foundation students, because it says higher here. Sorry for the noise, but. There's the book that I'm using, GCSE Chemistry Revision Guide, AQA GCSE Chemistry Revision Guide from Caboodle. That's the book I'm using. Showed that there we go. Showed you that a lot of times, obviously since the start, I think. But and so today we're doing C4.9 volumes of gases, and you can see it's for higher as well. You can see higher for today. It's higher, triple science higher, so I'm pretty sure it's not for foundation students doing triple science. But it's definitely not for combined science. This is for triple science students only. And so I think let's begin. It's actually quite a nice section, not very hard, and it's the last section of the book. Not last section of the book. Wow, we finished the chemistry content. No, we haven't. It's the last section of chapter 4. Sorry, and then we're going to go on to we're going to go on to chapter 5 after that. So so let's begin. So at the same temperature and pressure, equal numbers of let's start again. At the same temperature and pressure, equal numbers of moles of any gas occupy the same volume. Yeah, we know that. So you might not know that. So basically, you might not know that. But basically, at the same temperature and pressure, at the same temperature and pressure, what happens is that equal numbers of moles of any gas occupy the same volume, basically. So what that means is, at the same temperature and pressure, 1 mole of nitrogen molecules, would occupy the same volume as 1 mole of oxygen molecules, just to give you an example. So then it says the volume occupied by 1 mole of any gas is 24 decimeters cubed at room temperature and pressure. Now, room temperature and pressure here, it says 20 degrees Celsius and 1 atmosphere. You need to know you need to know the room temperature and pressure. It's 20 degrees Celsius and 1 atmosphere. I don't know. I think actually when we do it's I don't really know about room temperature much here, because the room temperature I think we use like in A-level chemistry, it's actually I'm pretty sure we use for the standard conditions, we use 25 degrees Celsius or 298 Kelvin. But I'm pretty sure, you should stick to what the book says here. So 20 degrees Celsius and 1 atmosphere. Just remember that. So that's 20 degrees Celsius temperature and 1 atmosphere pressure. Now 24 decimeters cubed per mole is known as the molar gas volume. So in 1 mole of any gas at room temperature and pressure, so at 20 degrees Celsius and 1 atmosphere, 1 mole of any gas would occupy the same volume, which would be 24 decimeters cubed or 24,000 centimeters cubed, because obviously to go from decimeters cubed to centimeters cubed, we multiply by 1,000, so 1 decimeters cubed is 1,000 centimeters cubed, so 24 decimeters cubed is therefore 24,000 centimeters cubed. So hopefully that makes sense. We've been through that before. Then you can use this equation to calculate the number of moles in a given volume of gas. So, and you need to know this equation. So at room temperature and pressure, the number of moles of any gas, equals the volume of gas, which is in decimeters cubed, divided by 24 decimeters cubed. So that's for the number of moles of gas. So you say number of moles of gas equals volume of gas in decimeters cubed divided by 24 decimeters cubed. So here's a question: how many moles of oxygen are present in 48 decimeters cubed of gas? Well, the number of moles of oxygen, oxygen present are the volume, which is 48 decimeters cubed, divided by so volume of the gas, which is 48 decimeters cubed, divided by the molar gas volume, which is 24 decimeters cubed. So that's just 2 moles. So I don't need to do any calculation there. I don't need to really show it on any kind of paper or anything. It's quite easy. It should be 2 moles of oxygen basically there for the answer. 48 divided by 24 gives me 2 moles. So gives us 24. Gives 2 moles. 48 divided by 24, and that's fine. Then here's a question as well. So calculating the volume of a gas from its mass. So here's a question. So in the worked example, So what volume of gas is occupied by 2.2 grams of carbon dioxide? And carbon dioxide has an MR, or relative formula mass, of 44, because obviously carbon has a relative atomic mass of 12 and then oxygen has 16, but 16 times 2 is 32 because it's CO2, so it's O2, so it's 12 plus 32, which gives you 44. Just to explain that there. And the relative formula mass, the relative atomic masses come from the periodic table, and the sum of those relative atomic masses give you the relative formula mass of a specific compound basically, and it's the top number of the periodic table. So I've gone through that before. So it says obviously work out the number of moles of CO2 that are present, and you'd expect to do that. You would whenever you have mass and whenever you have the mass and then you have the molar mass or the relative formula mass, you should instantly be thinking like, ooh, I need to work out the number of moles. Like that's what I need to be thinking now. So number of moles equals mass over MR. Remember the mass was 2.2 grams of carbon dioxide, so it's 2.2 divided by 44, which is 0.05 moles. So hopefully that makes sense. And now we worked out the number of moles, then we just need to work out the volume. So we know the equation, the number of moles of gas now, we've been through it. So number of moles of gas equals volume of gas in decimeters cubed divided by 24 decimeters cubed. So rearranging that for the volume will mean that the volume of gas in decimeters cubed equals the number of moles times 24 decimeters cubed. We already know what the number of moles is now. It's 0.05 moles. Timesing that by 24, which is the molar gas volume, and that gives us an answer of 1.2 decimeters cubed. So this is quite straightforward, it's not very hard. And in fact, I'll just show you the questions here. I'll just show you the worked example here. And this was basically all the working out they did for the worked example. I don't think I really need to go over that much. It's quite a straightforward example, really. You're working out moles, and then once you've worked out the moles, you're just rearranging the the equation that we just learnt today. Number of moles of gas equals the volume of gas in decimeters cubed divided by 24 decimeters cubed. And because this is for triple science students and for higher students, you need to be very familiar. You need to be very competent. I think that's the word. You need to be very good at rearranging equations. It's a basic GCSE math skill. So you should be very confident in doing that, and as long as you do that correctly, and you know the equation that you're using, and you substitute the values incorrectly and stuff, your calculation will be correct. So So then it just says, so 0.05 moles occupy 0.05 times 24, which is 1.2 decimeters cubed. So that's fine. So that's the volume of carbon dioxide gas in, basically by 2.2 grams of carbon dioxide. So hopefully that makes sense. Then calculating volumes of gas of gaseous reactants or products. You can use a balanced symbol equation to find volumes of reactants and products in a reaction involving gases. So because the same number of moles of gas occupy the same volume, the ratio of the numbers of moles in the balanced equation will be the same as the ratio of volumes of gases involved. So if that doesn't make sense, we're going to just look at this example. So for example, we have H2 plus Cl2 gives you HCl. But you need to balance the equation. So because it's H2 plus Cl2 gives you 2 HCl, because you're going to have to put the 2 there so that you have two hydrogen atoms on the left, 2 on the right, and then 2 chlorine atoms on the left, and then 2 on the right. So it all balances basically. So the ratio of moles of hydrogen to chlorine to hydrochloric acid, so HCl, is 1 to 1 to 2, because it's H2 plus Cl2 gives you 2 HCl. So that means if you have 100 centimeters cubed of hydrogen, the ratio of gases will be 100 centimeters cubed of 100 centimeters cubed H2 to 100 centimeters cubed Cl2 to 200 centimeters cubed HCl. So hopefully that makes sense. I'll just show you it here. It's just ratios basically. You're balancing an equation. Here you go. You're balancing the equation. Then all you're doing after that is you're just kind of after that, if it's literally just seeing if it's 1 to 1 to 2. That means if you have 100 centimeters cubed of H2, you're going to have 100 centimeters cubed of Cl2, because they're in a 1 to 1 ratio. But you're going to have 200 centimeters cubed of HCl, because the hydrogen and the H2 and the HCl are in a 1 to 2 ratio. So you just times it by 2 to work out the volume of that. That makes sense. Hopefully, it's not very hard at all. And then here it just says, here's the second question. So the second question, which is the last question of the section, it just says 5 moles of oxygen gas are needed to burn 1 mole of propane gas. Calculate the volume needed to burn 2 decimeters cubed of propane gas. So here, what we're going to need to do is I'm going to have to bring my paper here actually. I'm going to have to write down the equation, because I'm going to have to think about this one. It's not very hard, it's just a thing of thinking about it. So 5 moles of oxygen gas are needed to burn 1 mole of propane gas. Calculate the volume of oxygen needed to burn 2 decimeters cubed. Alright, so I'll see that. So here we have, so let's see this equation. So propane is obviously C3H8, and we're reacting that with O2 to then produce CO2 and H2O. And this is just then balancing the equations. So I'm balancing it. You should be pretty comfortable with actually being able to balance equations. That shouldn't be a very difficult topic, really. It shouldn't be a very difficult task. So we've gone through it before, so I'll just balance it here. And then obviously if you have 4 here, then that means we must have 4 plus 6. That means we have 5 over 2 here. So this is my balance symbol equation for the reaction between propane and oxygen, because it's a very what is it called? It's a very basic scale balancing equations. It's a combustion reaction. Then it says, so 5 moles of oxygen gas are needed to burn 1 mole of propane gas. So we know that, yeah. Calculate the volume of oxygen needed to burn 2 decimeters cubed of propane gas. I'm going to have to think about this 1 minute. I'm just thinking about this. 5 moles of oxygen gas are needed to burn 1 mole of propane gas. Calculate the volume of oxygen needed to burn 2 decimeters cubed of propane gas. Alright, so let me think about this. So this is 1 mole of propane gas, 5 moles of oxygen produce this. Calculate the volume of oxygen needed to burn 2. Okay, so I'm just thinking about this one. Sorry guys, it's taking me a bit of time to think about this one. But this should just be, for the volume over 24, 1 mole of propane gas. Alright, so 1 mole we've been told, and 5 moles of oxygen gas. Why am I not being able to do this? Wow, I'm just thinking about this one. If we have 2 decimeters cubed of propane gas, oh, I'm so silly, guys. It's just such an easy question. Wow, we've literally just been through this. When we have, when we look, all of these are gases as well. Basically, all of these are, not all of these, sorry, in the equation. Oxygen and propane are gases. I don't know why I took so much time, actually. It took a couple of minutes for no reason. There's 2, obviously, we have 1 mole of oxygen gas, 1 mole of propane gas reacting to produce, reacting with 5 moles of oxygen gas. So that means if you have 2 decimeters cubed of propane, then that means you have 2 times 5 decimeters cubed of oxygen. Basically, the volume of oxygen. So that's just going to be 2 times 5, which is basically 2 times 5, which is basically 10 decimeters cubed. So I don't know why I took so long, guys. I'm really sorry about that. It's not really good for my reputation, is it? But there you go. Because the reason why is because obviously when you can see in the equation as well, if you have 1 mole of propane and then you have 5 O2s, if you have 2 decimeters cubed of propane, you're going to have 2 times 5 decimeters cubed of oxygen, which is just going to be 10 decimeters cubed of oxygen. So I don't know why I took so much time in working that out. I'm going to now look at the answer. I'm going to look at the answer and see if I'm correct. So it's 10 decimeters cubed. Yes, it is. Sorry, it's my brother here. He's trying to disturb me. No, I'm joking. But he's a sweet boy. So now I'm just going to go through the key points. Just to the study tip. So you should always include units in your answer when calculating volumes and masses. Then for the key points, just to finish off. So a certain volume of gas always contains the same number of gas molecules under the same conditions. Yep. The volume of so we know that because it says certain volume of gas contains the same number of gas molecules under the same conditions. So that's under same 20 degrees Celsius and 1 atmosphere, room temperature and pressure. You can have equal volumes of gas for you'd have equal volumes of gas molecules basically for anything you're looking at. So it could be nitrogen molecules, it could be oxygen molecules. You'd have equal volumes of them at room temperature and pressure. Remember, we've been through that before. The volume of 1 mole of any gas at room temperature and pressure, you need to know this is 24 decimeters cubed, which is 24,000 centimeters cubed. And finally, you can use the molar gas volume and balanced equations to calculate volumes of gaseous reactants and products. And we've been through that as well, molar gas volume balanced equations to calculate volumes of gaseous reactants and products. All products, like we've been through in the last example, which I took like one or 2 minutes extra than I actually needed to. It's a very simple one. Sorry about that, guys. And have I been through the study tip? You should always include units in your answer when calculating volumes and masses. So and there were no keywords. There are no keywords in this section, and there aren't any keywords in the last section as well. I don't think I mentioned that in the last section in yesterday's video. But that's the end of the section, guys. I think I'll just show you this. Question here, the question that we were doing, the question that took me 1 or 2 extra minutes. The second one you can have a look at it for yourselves. But it's a very easy question. I don't know why it took so much time. Sorry, guys, again. I'll try and put the links up to the videos from C3.2 to C4.9 by today on my website. And we're done with chapter 5. We're done with chapter 4 now. Tomorrow we're going to be doing. From tomorrow we're going to be starting chapter 5. And now you can have a go at these questions for chapter 4. These are the practice questions. Are these practice questions? Summary questions. Sorry, summary questions. You can have a go at them if you have the book 36, page 36, and then page 37 has the summary questions. So it's page 37 and page 38. Page 38 as well has summary questions which you can basically try out. So it's very good, this book, so you can just try them out, guys. So make sure to share, like and subscribe, and turn the notification bell on if you haven't already, so you're notified updated when I upload new videos they can watch. And I think I'll see you in the next video, guys. Tomorrow we're starting chapter 5 C5.1, which is all about, what is it about? Which is called the reactivity series. So that's going to be interesting. Until then, have a nice day, guys, and I'll see you tomorrow. Thank you very much, guys.